Before I begin, just a quick raise of hands. How many of you are in any way acquainted with Clojure? All right. And with the Java in general? Great. We'll have some common ground. So let's begin. What is Clojure? Well, it's a dynamic language. It is LISP-based, and it's running on the Java virtual machine. That's the basic premise of it. It is very young. Rich Hickey is the creator of the language, and he released it in 2007 after initially working on a Lisp machine for the CLR. Then he switched tracks to the JVM. But since Clojure, or Clojure, which it's supposed to be pronounced actually, is a Lisp dialect, so it has roots in the 1950s. Really, these are really your father's parentheses, as they say. And the features of such a language is that it's functional, well, basically mainly functional. The core of the idioms is to use functional programming. And it's homoiconic, meaning that the syntax is represented in its own, in the data structure of the language. So these enable very powerful features like macros. It also focuses on immutability, given that it's a functional language that's sort of expected. It has very efficient, persistent data structures so that you can add things to maps without incurring the debt of copying everything and so on. And it's generally very powerful, like most Lisp systems are, since you can compose functions and use macros to generate DSLs very easily. Also, Clojure focuses on concurrency and is very efficient for working on multi-core processors by introducing the explicit separation of identity and different states of something identified. You can work easily with concurrency. It's also pragmatic, so it has very compact syntax and some syntax for high-level collections, which differ somewhat to older Lisp dialects, who mostly are almost over-encumbered by parentheses. There are some cases where Clojure uses a more tight syntax to reduce the amount of parentheses actually needed. And it's a symbiotic language with a host language, and the primary implementation is using Java as a host language, and the entire interoperability is designed to work with Java specifically, but it has also been hosted on the CLR, and there is also an implementation in Python currently going on, so it is sort of possible to use the core of Clojure on different host languages, and that's also a design by design. It's intended to be used basically for any kind of programming problem. It's a general purpose language. So in theory, you can just use it instead of Java for any problem where you normally use Java, with some limitations in speed, like in most dynamic languages, although there are ways to get around that in Clojure as well. I mainly worked with it to process data. I'm experienced in XSLT, and I've churned data with anything from Perl and awk to Python, and have transformed data in many situations. And I found Clojure very applicable to that problem domain, given that it's functional, so you always know that you're transforming states of information. So, the JVM, is that a good choice? Well, it depends. It's a very powerful and well-spread platform in the galaxy, so you can rely on it being a very good workhorse for many things, and it's been tested and battle hardened for many years. So it's a very smart choice of a host language. And many things in that community is open source as well, as you probably know. So there are lots of libraries to use for any kind of problem domain. And the Clojure is fun. It's pure fun. It's not fun by incident. It's fun because it really appeals to the purity of Lisp syntax. It looks like this. This is, you've probably seen Lisp and know the shape of Lisp. It uses prefix notation, which is a very powerful ID. It makes any kind of code uniform. It becomes very easy to abstract things and compose them. And code, even when very complex, is quickly predictable to read. Even the macro system is so predictable, so you understand the shapes of things very easily because you always know the structure of the code. And you will never have any problem with operator precedence because you always have to use the parentheses. Also, this is because these expressions are real lists and the code is actual data. So it makes it very easy to metaprogram with macros. And if you find a hard time reading these expressions because you normally say 1 + 1, you just stop thinking like that and think add 1 and 1, and suddenly everything becomes clear again. So just shift your mindset one step to the left and it all works again. So let's just take a quick peek at the basic syntax items available to you. You have regular scalars, and you have collections for making compositions of data. And then there are certain special forms which are evaluated specially to enable the core language to work. The basic types, the primitive types, are characters and strings, numbers, booleans, the nil value, which is nothing. And you also have ratios, so you can work with fractional numbers without losing stuff by truncation. If you use regular floats, you've seen that that's a real problem in mathematical computation. So there is a built-in scalar type for ratios, which looks like that. And you have regular symbols, which you use for names, for variable names and function names. You're allowed to use certain special characters which aren't normally allowed in other languages. You can use plus or question marks and dashes. Also, the dot is a special form which is used for the Java interoperability, which we'll look at a bit further on. And then apart from regular symbols, you also have keywords, which begin with a colon and stand for themselves. They never belong to a namespace, they stand explicitly for themselves. And they are used commonly as keys in data structures, but also by certain functions and operations as directives. So let's take a peek at the collections. As mentioned, you have the regular list syntax, which is used for evaling expressions. So by design, the Clojure engine interprets and evals these expressions so that print line hello results in the printing of hello. This is actually one of the side effect functions, so it also returns nil. But you can quote them with a single quote, and then you can access this list as a regular data structure, and for instance, take the first item of it like that. Notice that Clojure calls first and not car, so you don't have that problem in Clojure. But if you're going to work with arrays of things, you normally don't use the simple list collection. You use vectors instead, which use the bracket syntax and looks like this. The difference is that you have random access with the regular O1 speed in these, whereas lists are actually linked lists by implementation. So you use vectors when you need to use general purpose arrays. And for objects or structs or records, if you will, you regularly use hash maps like this. You can use anything as a key, but you normally use keywords as a key unless you have a specific reason for using something. You can use hash maps like any kind of lookup tables. You can put anything which has a hash value into them, like a regular string or even a function which has its ID as a hash. But normally you use keywords, and hash maps indicate one of the design decisions that Clojure has made, which is that in certain cases it throws away explicit grouping of things. So as you see here, you really have 4 items, and you just group them together pairwise. There is no ambiguity here. You know that hash maps always uses a key and a value, so there is no need for anything else. It almost looks like it's falling apart, but it never will, because you always know how the shape should be in these, and you will get errors if you try to do something else. You also have sets, where each item in a set has to be unique, so if you add a string unique to this again, you will get the same set back. And the difference is that you use a pound sign before the curly braces. You can use commas if you want to, but commas are just white space. So they mean just as little as white space. But just as you want to indent your code for readability, in certain cases you want to use commas to make things more clear. That also means that you can put 30 commas in here and it doesn't matter because it's just white space. So use them for readability and nothing else. And then we have the special forms. The core special form is the def, which binds a symbol in the current namespace to a value. Pretty simple and straightforward. Obviously a side effect, so it's not an expression per se. It's a way to build up your current namespace with values for the symbols. If is also a special form. The if expression takes the predicate, and if the predicate is true, it evaluates the first expression after that. If it's false, it evaluates the last. And apparently true is true, and this is nothing dangerous. But if true were for some reason false, you would divide 1 by 0 and get an exception. This is how you define functions. Again, if you've seen older Lisp dialects, normally you don't have the vector syntax, and argument lists are expressed with parentheses, but since Clojure thinks that too much parentheses becomes hard to read, it has decided to use the vector syntax for the argument list. And all these small design decisions really helps to read large amounts of Clojure a bit faster than common Lisp, for instance, as far as I've seen as well, at least. Of course, you want to name your functions to be able to use them, although you can pass them around as well, but normally you build up your namespace with named functions. And if you want to, you can just define the symbol greet to be bound to the function expression, but normally you want to use the defen macro. And this is a very simple and easy example of how Clojure uses macros to create compound expressions. So this expression defines the function greet and expands to this form. course, you want to use local names when you build bigger functions, and for that you have the let special form, which to a certain extent looks like the hash maps in that it groups pairs of things. So you have the symbol greeting bound to the value hello, and then you have out bound to the expression of the string concatenating greeting, the string and the name. And as you see, you can use the names occurring previously in the same let vector. So this is a way to create local variables. And everything evaluates to the body of the let expression, and the function evaluates to its body. So there should be nothing complicated with this. But as I said, you often pass around functions to other functions. And if you do that, after a while you get bored of the explicit and argument list syntax, because you just have to name the same variables over and over again. And for that reason, you have the lambda syntax sugar, which uses a pound sign in front of an expression. And then this becomes a function which takes arguments, as many arguments as there are percent signs within the expression. And if you have more than one, you number them like this. If you only have one, you only need 1% sign. It's really nice. And fun. There are some more sugar. We are not going to look at all of them, but just so you know that there is syntax sugar for regular expressions, and for concurrency, which we'll look at later on, you have, instead of invoking deref for dereferencing references, you can use the @ sign instead. And the rest is just eval apply. So that's the basic shape of Clojure. So how do you use it? Well, as we've already seen some examples of usage, this is how you normally use vectors. You take the first or the rest of the items instead of cutter. Also, vectors are callables, so they are functions, so you can call them with an index, and you will get that item out. So depending on if you know that you have a vector, you can use the latter form. If you add to collections, or actually create new collections from old collections, you use cons to add them together, and con to add just one item to a collection. And cons and con work also for lists, but since lists, the raw lists are linked, you actually add things to the front of them when you use the same operations. But vectors are mostly the way to go. There is, of course, many functions which take other functions as arguments, map naturally, and it looks like this. Inc is a built-in function. You have the explicit variant below, which is a lambda, which increases the one argument it gets with 1. As you see here, the result is actually expressed as a list and not as a vector. And most sequence functions in Clojure are represented like this. You don't get the same type back when you map things. You just get something you can iterate over. And linked lists are more efficient for that, for obvious reasons. Reduce, of course, nothing complicated here. Well, you should know that if reduce is invoked with a function and one sole argument, it starts by taking 2 items from the sole argument and applying them to the function, and then it applies the result with the next item and so forth. If you have 3 arguments, you can, the first is the seed value. For more complex expressions, you can use 4 comprehensions, you might be acquainted with if you used Haskell or Python, for instance. Maybe you have them in Erlang as well. here you see an example of how Clojure uses keywords as modifiers for certain expressions. So instead of just looping over the range 1, 2, but not including 7, it has a directive called when, which uses the keyword syntax, and this modifies the for loop. There is also a let directive, so you can transform the value within the for comprehension before you use it. So you can use that for even more complex for comprehensions. And you can also use several loops together, so you can build a coordinate system, or an image, if you will, by looping over x and y simultaneously. So you use for x range 1, 2 width, and for y 1, 2 height in the same for expression. So you combine them. Clojure is by default lazy, so almost anything you can loop over is lazy. So there are no problems with infinite sequences, and there are built-in expressions for creating infinite sequences, like for instance repeat, which is an infinite series of ones, and iterate, which applies a function over and over again. But you can see that filter and map reduce and for comprehensions and every kind of looping construct just takes one item at a time. So you can use this to, for instance, work with big files. Read lines is another example of an expression which takes one line at a time and doesn't read the entire file at once. So let's look at how you use maps. Normally you use them like this, so you create value objects very efficiently. Here we have a list or a vector of 2 objects, literal objects, which represent persons with an ID and a name. And then we take the first person from that, and we pick out the name. So just as vectors are callable, maps are callable, and you can call them with a keyword, and then you get the value for that keyword out of the map. But you can also call keywords. So actually keywords invoke the thing they are invoked with themselves. And they return nil if the thing they are invoked with is nil. So it's a very soft way of working with unstructured or semi-structured data, lossy data. And as keywords are functions, you can of course send them to other functions as functions. So you can use map, so you can get every name from the sequence of persons very efficiently. But if you get bored of writing literal objects like this all the time, there is a macro called def record. And you define a name for it, and you, as symbols, name the keywords which will be created for you. So you will get something which behaves like a map with the keywords ID and name in them. But you also get a constructor function, which you see invoked here with person dot. That's actually the same way you instantiate Java classes. You write the class name dot. You can use new as well, but this is the idiomatic form. And for interoperability, actually records become Java classes, but their fields, ID and name, public. There are ways to generate Java objects with getter, etc. as well, but this is the way to use it to get the keyword thing working. So these are, you can start off with literal hash maps and then replace them with this syntax. And you can pack up things. You can take 2 items from a sequence at once, and using the let expression like this, you can take 2 items out and bind them to names. You can also use a map literal, where you actually put a symbol on the left-hand side and the keyword on the right-hand side. By that, you destructure a map or a record and take out the ID and the name like that. Things are immutable, of course, so if you try to associate the name Neo to an object, that object won't be modified, but you have to use the computed value of the associate invocation to actually get a new value, so things are never changed in place. I don't think we have time to discuss namespaces in details, but you should know that namespaces are an important part of Clojure. We don't have so much time, so let's skip ahead. I think that you know how to think functionally, so this isn't really relevant for most of you. Instead of imperative programming, pulling levers and switching things.
We have 20 minutes.
20 minutes? All right. I thought you said 5. Okay, great. Then, well, namespaces. No problem. It woke me up a bit. Well, you always have a namespace, and just like def sort of creates something in place, namespaces declare the current namespace, and regularly you create one namespace for one file, but semantically this is how it looks. So you would say that this is the namespace sum.cli, and for it you require things, and in this case we also alias them, so we get some core namespace and we call it core. And then you use slash to access items within core. Here you also see a bit of syntactic sugar for variable length arguments, which is the @sign function. So when you invoke things like that, you don't put them in collections, you just put them one at a time, and then you use the @sign to access the entire argument list as a sequence. Did I say at? I mean and, of course. That's apparent. So, this is how you compose data and you compose functions together. You start with simple data, and then after a while you might use macros and def records and things like that to create abstractions and build up more complex constructs behind macros. And since things are immutable, you always get a new value from invocations, and you chain these together to transform your data into new expressions. And if you think in Java, you have to leave that behind because you can't add and remove things in place. Normally you stop doing that, and instead you compose things, and everything's become a succession of states over time. Which leads us to concurrency, because sometimes this is not possible to do. You have to modify some shared state somewhere, and Clojure, of course, has support for that as well. It explicitly models things as transitions of states over time, and what we've seen so far is values. Everything is a value, and the value is a state. But you also have the concept of an identity, which you can reference, and identities can change over time. And under the surface, Clojure uses software transactional memory to do this, to isolate points in time from each other. But I won't go into the nitty-gritty of how that works, just so you know that this is the way to do concurrency. And for the simple case, you have atoms, which you can use, for instance, like this, a simple counter. So every time you invoke next item, you get a string with the last part incremented. And to do that, Clojure invokes swap on an atom, and an atom in this case is the item counter, and swap takes the atom and the function, and then it changes the value of the atom to the result of applying that function with the value, initial value of the atom. And then you use the @ sign as a syntactic sugar for deref to get the value out of the atom. So this is a way to explicitly model changes of things. A similar construct is the references, which you use with the function doSync, and this changes them simultaneously together. So from the outside, they are changed at the same instant in time. Although we pick them apart and then we doSync and alter them one at a time, we have to do it within the doSync block, and when we do that, they are to an external observer changed at the same time. As you can see, both atoms and references can hold any kind of data structure as a value. It can be arbitrarily complex. In this case, we have a hash map in there. And finally, you have agents, and these are you use them for asynchronous programming. So an agent, again, holds a value, and then you send something to them, and what you send is a function and optional arguments, and then that function is applied with the agent as the first value and the optional arguments as the rest. And the agent itself has its value changed to the result of applying that function. And now we get to Java, the terrible things of Java land. These are hideous beasts, but you can work with them in Clojure. They are, of course, by nature, not adhering to concepts of immutability and explicit time, but you can still interoperate with them fairly efficiently with syntax sugar. And since you always invoke functions with values in Clojure, this is the way to use Java from within Clojure. What we do here is that we create a string by resolving the JavaNet URI instance using the example.org/a URI with the string b. That's how you read the entire expression. And from the inside out, of course, you create an instance by using the dot suffix to the name. And to invoke methods on objects, you use the dot method name with the object as the first argument. So let's look at how this works for some simple concurrent programming. First, we import things from Java IO and JavaNet into our own namespace. And then we define a getURL function, which invokes lots of things in Java instances. It always gets noisy when you use Java, but at least this way it's more fun. Some things to notice here is the do-to, which is invoked on line 2, which actually takes as the first argument an object and then a sequence of method invocations where the first argument is implicitly the first argument, and then it returns the same object. Since in Java you often invoke things to change the state of objects, this is a way to visually make it look like something functional. Of course, you still change the state of the object in place, but at least you isolate that horrible action within a do-to expression. And the with open is very nice because it creates something and then closes it finally, regardless of if there is success or failure. And finally, we create a bunch of agents by looping over the URLs we send in, and we create an agent which holds the URL. One agent holds one URL. And then we use a do-sec, which is a way to force looping, because normally everything is lazy in Clojure, but with do-sec you actually do things instead of picking them out one at a time when you need them. It forces the evaluation. So for each agent, we tell them to invoke get URL with themselves. And then a wait for actually makes the current thread wait for any other thread in this list to complete with a timeout of 5 seconds. And finally, for everything, we deref everything and send them back. And then we get a sequence of fetched web pages, which have been fetched by separate threads. Kind of a tight way to do programming. Compare this to the equivalent in Java, and you'll see that this is way more fun.
How come you use the vector syntax instead of list syntax to pick out one value from the rest of the values?
The do-sec uses the same syntax as the for comprehension.
Oh, okay.
So the first is the name bound to each item in the list, or the sequence. It's the same with the let. So every time you name something, this is the idiomatic way that Clojure macros and functions use to express that notation. After a while, it's funny, but after a while you start to sort of see the reasoning behind everything that Clojure has done. And these little differences make sense and makes code a bit more easy to quickly read. And finally, let's take a look at how you do the equivalent of interfaces. Because as you've seen, invoking Java can be a bit noisy at times, and you might want to have a more Clojure idiomatic way of doing things. So imagine that you have DOM elements, actual Java DOM elements, and you want to use idiomatic Clojure functions on them. So you want to define get name, get attr, get idle events. Then you can define a protocol. And a protocol is a group of functions which you can then realize somehow. So you actually define functions, and you can require this construct from a module and use in your code, and you just use the get name, get attr, and get child elements as regular functions. But here we don't have an implementation. Instead, the first argument always has an explicit type, of course, and to realize a protocol, you say that for a certain type, this is the way to implement the protocol. So for the DOM nodes, you implement them like this. And then you write the Java incantations to actually realize the protocol. This is a very powerful way of doing indirection and defining contracts on your own terms. And you're also able to implement protocols with various different things being sent in under the hood. And this doesn't only work for Java. You can use these mechanisms for any kind of thing in Clojure. And if you recall the structuring of maps, there is mechanisms for multi-methods in Clojure, which actually matches on arbitrary things which you send into them, and you dispatch to various implementations depending on the shape of things. This is sort of like pattern matching in Erlang or Haskell. It's not as powerful, but it gets a long way to separating contracts and implementations for different kinds of values. It's extremely powerful in the general sense. And it makes it very easy to adapt strange Java code to idiomatic Clojure code. So, for real then, if you want to use Clojure, what do? Well, use Leiningen. Leiningen is a build dependency handling tool. Under the hood, it actually uses Maven. So you get access to the dependency mechanisms of Maven by using Leiningen. So you define a project file which is written in Clojure where you declare dependencies, and then you use things like line depths to fetch all the dependencies. So you can compile things, create Uber jars if you want an executable jar file with every dependency included. And there are modules, so you can use, for instance, the Ring, which is a web framework for Clojure. And if you're writing web applications, you use the Ring plugin to start a local server, and it will reload when you change your Clojure code, things like that. So Leiningen is the go-to tool if you want to try things out. And you get the read line eval print loop by the REPL invocation. You can always use Clojure just by writing CLG and get the REPL, but with Leiningen you get the dependencies in your current project on your class path and things like that, so you can actually tinker with libraries and stuff. And it has command line history and coloring and things like that. It's a very nice tool. And for editing, there are lots of plugins. I use Vim myself, although Clojure is the first time I've actually even considered really trying Emacs, because as everybody knows, if you love Lisp, you should use Emacs.
We should always use
But regardless if you do or not, they both have excellent plugin support for using Vim and getting completions and interactive REPLs within the editor and stuff like that. And if you like to wait for your editors to start up for a while, you can use ID, and I even believe that you can, if you really like to take a coffee break, probably use Eclipse for editing Clojure as well. But I'd recommend the first two. And of course, although it's a young language, everything happens fast on the web today, and there are lots of resources on the web, documentation, examples. And if nothing else, even if this doesn't appeal to you, I really recommend that you take a look at the presentations filmed where Rich Hickey speaks about the philosophy behind his decisions. Are We There Yet is an excellent expose of how he thinks about time and the separation of identity and state, where he references Alfred North Whitehead and other philosophers a lot, and it is a fairly deep reflection on the nature of time and state. And the other one I really recommend is Simple Made Easy, which is also a very brilliant piece on the difference between things that are easy because we're accustomed to them and things that are simple. And by that I mean mathematically simple, purely simple. So, have fun with Clojure. Thank you. Any questions? Shoot. Yes?
Yeah, okay. Let was partly recursive, but is it completely recursive? Can you have recursive non-like version?
Yes. Yeah, there is actually I think that it's a special form or a macro, I'm not sure, but it's a recur invocation, which invokes the current function with the arguments. So it's explicitly recursive. I think you need to do that because symbols, you have to define the symbol name and then define the implementation. So there are tricks like that, but the recur is in a way to explicitly do that.
The swap instruction, didn't it return something, the previous value or something? Because otherwise...
Yes, it's synchronous, so that you get the value there immediately.
Value back, right?
Yeah.
You explicitly read.
Oh no, right. I think that it. Sorry, it's synchronous, but it doesn't itself return anything.
It doesn't return anything.
Well, I'm not really sure if it does. You don't.
If you have two threads there and both of them are incrementing counters, then they will have icon 1, icon 3, icon 3. Okay.
Yeah.
And the last question, lazy relation, is it really good choice? Is it just a cool choice?
For this.
It's not a 3-minute answer.
Well, I think that it's good in general. I've used Python a lot, and Python has switched incrementally its design from using things by default as lazy evaluation, lazy loops, iterators. In general, I think that it's a better design choice, although it comes with a cost at times. But it's much easier to shoot yourself in the foot or get a memory overload if you don't have it by default.
With the prototypes.
The protocols.
Protocols, yeah, sorry.
Yes.
You define the protocol. Yeah. Then the next slide, when you implement it, is there any check that it follows it, or is there checking that you're actually following the protocol then, when you implement the protocol?
Yeah, there is, but there isn't much of a protocol here in terms of what you need to check. It checks that you implement all the names and that the argument lists. Well, you can have variable arity for different things as well in Clojure, so it checks that.
But they're in the same name, those functions, they're in the same namespace as the one you declare the protocol in.
Yeah, that's an interesting observation, very good one. Yes. The symbols here, the extend type is a macro, and the symbols are just checked to conform to the names in the protocol, whereas the DOM access is a live symbol, if you will, so you have to import it and use, if you use aliases, you have to use something /DOM access, but you don't have to namespace qualify those symbols because they are always intended to map to the names in the protocol.
All right. Thank you again.
Thank you.